Have you ever really thought about what's happening when you look through a microscope? You might think you're just seeing a bigger version of something tiny, but that's not really it. What you're actually seeing is a reconstruction, kind of like a ghost image, built entirely from scattered light. So today, we're going to follow a single beam of light on its wild ride and really dig into the physics of how we see the unseen. So, how in the world does a simple piece of glass, something you see every day, reveal a whole hidden universe? Well, the answer is all about following the path of light. We're going to start with its super weird and mysterious nature and track it all the way to the final image it creates. Okay, so our journey starts with a real head scratcher. Before we can even get to lenses and images, we've got to tackle this weird dual nature of light. Is it a wave or is it a particle? The wild answer is, well, it's both. Yeah, light basically has a split personality. On one hand, it travels through space like a wave, with a wavelength and frequency. But the second it actually hits something, like a camera sensor or even your own eye, bam, it delivers all its energy in one concentrated punch, acting like a tiny particle called a photon. And you got to get this, because this whole wave-particle thing, it's the foundation for literally everything else we're going to talk about. All right, so we kind of get what light is, but how do we control it? That brings us to our first tool in the toolbox, the lens. We all know lenses focus light, right? But how? It's all about bending its path. The fancy word is refraction, but all it really means is that we're changing the light's direction as it goes from the air into the glass and then back out again. And this bending isn't just random chaos. Nope, it follows three super predictable rules. Think of them like traffic laws for light rays. Rule 1, a ray going right through the center of the lens, it just keeps going straight, no deviation. Rule 2, a ray coming in parallel to the main axis gets bent right through a single focal point. And rule 3 is just the reverse. If a ray passes through that focal point first, it gets bent so it travels out parallel. And if you know these three rules, you can predict exactly how a lens will wrangle all that scattered light into a nice, sharp image. Okay, but here's where it gets really cool and a little weird. Before the lens can even think about making an image, the light that interacts with an object does something totally unexpected. It's not just casting a shadow. No, it's creating this incredibly complex, hidden pattern. So picture this. As a wave of light hits the edge of a tiny object, it doesn't just keep going in a straight line. The wave actually fans out, it spreads, kind of like how ocean waves bend around a post in the water. And this spreading action, it is absolutely key to forming an image. And of course, it has a name. That's diffraction. And here's the main takeaway. The object isn't just a roadblock for light, it's an active participant. It scatters the light into this super intricate and, kind of messy looking pattern. But, and this is a huge but, that pattern isn't random noise. It's actually a code. It's a secret blueprint containing all the information about the object. So, okay, if this scattered light is a hidden blueprint, how do we, read it? Well, that's where the lens comes back into the picture. Its real job isn't just to make things look bigger. Its most important job is to be a decoder, to take that scrambled pattern and turn it back into a picture we can actually recognize. And this whole thing is a pretty profound idea when you think about it. A lens is basically a two-stage optical computer. Stage 1, it takes all that messy, diffracted light and sorts it into a nice, orderly pattern of spots. This happens at a specific place called the back focal plane, and each little spot holds unique info about the object's structure. Okay, then comes stage 2. The lens takes all those separated spots and recombines them. This is called interference, and it's where the light waves either build each other up or cancel each other out to perfectly reconstruct that final magnified image. And check this out. This is how we know the pattern is a code. There's this super interesting inverse relationship going on. When the little details on the object are spread far apart, the spots in that diffraction pattern are packed close together. But as the object's details get tinier and closer to each other, the spots in the pattern actually spread farther apart. The lens is literally translating the object's physical information into a whole new language made of light. So the big question is, how much of that code does the lens actually need to grab? Well, according to the physicist Ernest Abbe, the magic number is 2. That's it. If your lens isn't wide enough to capture at least 2 of those diffracted beams, that's the main one that goes straight through, plus at least 1 of the scattered ones, you get nothing. No image at all. All that precious information just vanishes before it can be put back together. Okay, so this whole process, diffraction, recombination, it all leads to one big final question. What's stopping us from seeing infinitely small things? I mean, why can't we just build bigger and better lenses until we could see like individual atoms with a regular light microscope? Well, the answer comes down to a really critical difference. See, the real challenge in microscopy isn't just about making things look bigger. That's just magnification. The real goal, the thing everyone's after, is resolution. And resolution is all about being able to tell that two tiny things sitting right next to each other are actually two separate things. Resolution, that's the true measure of a microscope's power. And what's so fascinating, what's kind of a mind bender, is that this limit isn't set by how good our glass is or how precisely we build our tools. Nope. It's a hard limit set by the very nature of light itself, by that diffraction process we've been talking about. And this fundamental limit even has a name. It's called the Rayleigh criterion. And what it does is give us a very clear physical rule for the exact point when two separate little spots of light blur together into one fuzzy blob. Okay, let's break this down. Because of diffraction, even a flawless, perfect lens can't focus light to a perfect, tiny point. It's impossible. It always makes a tiny, blurry disk, which is called an airy disk. So now imagine you've got two of these points, and they're super close together. Their little blurry disks are going to start to overlap. They're officially resolved, meaning we can tell them apart, at the exact moment the bright center of one disk lines up with the first stark ring around the other one. And when that happens, it creates a little dip in brightness between them, about a 20% dip. That's just enough for our eyes to notice. Get them any closer than that, they just blur into one single spot. And that right there is the absolute physical limit. Can't beat it. And this whole entire concept gets boiled down into one beautiful, elegant equation. The resolution, R, equals basically the wavelength of the light you're using, lambda, divided by something called the numerical aperture, or NA, of the lens. So what does that actually mean? It's simple. If you want to see smaller things, if you want a smaller R, you only have two moves. One, use light with a shorter wavelength, like blue or even UV light. Or two, use a lens with a higher NA, which just means a lens that's better at gathering light from wider angles. That's it. Those are your only options. They're the rules of the game laid down by the laws of physics. So the next time you look through a lens, just remember what's really going on. You're not seeing a direct copy of an object. You're seeing this incredible, careful reconstruction, that ghost image we talked about, built from a hidden code of scattered light that's been decoded and reassembled by a lens, all happening right at the absolute edge of what's physically possible. And it really makes you wonder, right? What other hidden worlds are just waiting out there for us to invent a new way to see them?